Hi class, I'm so excited. Today we are doing our bread and cheese lecture, and this is a lecture I have been waiting a long time to share with you. So when I'm not teaching chemistry of cooking, I'm upstate in New York working on my bakery. So my husband and I own a small wood-fired artisan sourdough bakery, and we produce bread and croissants here. So today for our lecture, we're going to take you through the bakery and talk about how we produce our breads and some of the unique properties that they have, as well as some of the science behind it. And then we'll do a cheese tasting where we're going to check out different cheeses and talk about how they're produced. Today is going to be really fun, a little bit different, and I can't wait to share it with you. And now I would like to introduce you to a little lady who's critical to our bakery. This here is Mom. So this is a giant vat of pre-ferment. It's a wild yeast sourdough. And all we put in here is flour and water, and you can actually see the bubbles. So if I just give it a little tap, you'll see some of the bubbles moving. And this is a living culture of yeasts and bacteria in a symbiotic relationship that we use to rise and flavor the doughs. So the first step to making any sort of bread is actually mixing the dough. And during this process, there can also be something called autolyse.
Mostly done, the word is used when you talk about like long fermentation dough. Is a period of resting after slightly mixing the dough for about a couple of minutes to combine all the ingredients. It's a period of rest in which those ingredients get to be binded more and then develop their own gluten, because that's important, and then that can go up to 20 to 30 minutes or 45 minutes depending on the product. And then because when we say long fermentation dough, we say less mixing pressure. So we let the dough relax, and during the relaxation period, the gluten get to be developed with production of CO2 and the enzyme consuming everything that they can, and that strengthens the bond of dough.
So now we know how gluten is formed as it's mixed and kneaded, but what is gluten? Gluten is two subunits, gliadin and glutenin, and these two molecules come together to form the world's longest molecule. And in this case, what they do is they give the strength to the bread. They give it both elasticity and plasticity, and this allows the bread to be soft, but also to hold those air bubbles. So we have to develop gluten, and we can do that in a few different ways: through autolyse, allowing the natural enzymes to work, but also through kneading. So here we have a focaccia dough. This is an oily Italian dough, and you can see as it's mixing, it's beginning to change. That gluten is being formed, and it's beginning to get a stronger structure. So just a few more minutes on this dough, and let's look at how it's actually changed. We can see it's much more of a cohesive mass. So now our baker has added the salt and rosemary to the dough. It also will inhibit the yeast fermentation. So the same way that salt is a preservative and stops bacteria and mold and yeast from growing, it will also stop the yeast from doing its initial fermentation. So we want to make sure that they're good in there and they get access to some of those sugars before we start adding the salt. And we'll see the dough as it changes just with the addition of the salt. And now we're streaming in the olive oil. This is the hallmark of a focaccia, is an excessive amount of olive oil in the dough. So now that the dough is fully formed and we have a solid gluten network, we're going to check for gluten formation, and a baker does this by doing what's called a window pane. So they're going to pull the dough and stretch it, and this allows the gluten to fully expand, and what we're looking for is for it to be super sheer. We want to have good gluten formation in that dough nice and sheer without ripping too much. We also make croissants. Croissants have a sourdough bread base and are laminated, meaning that flaky sheets of dough are created by pressing butter between the layers. Let's talk to Ben, Baker Ben, and see again how they do that exactly.
It's actually one of the longest fermentation as far as like dough is concerned. Based on how we mixed it the day before. We divide it, we cube it up if you want to call it, into like a big square chunk, and we let it proof overnight, and then so it will triple up in size pretty much. So following up the same reaction, the enzyme production and the CO2 being formed, and then that ensure that the dough is properly fermented, and the next day we degas it, take all that air out that has been produced overnight, and that air actually will have a very lactic fermentation smell, and it's like amazing how that smells, very good. And we degas it and we put in the freezer or in the fridge for the dough to reach a certain stiffness along with the batter, so we can start our lamination.
Okay, so now the dough has been degassed and shaped into a rectangle, and we're going to start what's called lamination. This creates puff pastry. Any kind of puff pastry is done in a similar fashion. So we start with our enriched brioche style dough, and we're going to encase it with a half of its current weight in butter. So if this is a 2 kilo loaf of dough, we're going to put 1 kilo of butter in there. And as we know, butter is a lipid, meaning that it is hydrophobic. It is not going to bond with the water. So the water molecules and the lipid molecules are going to be staying separate within this mixture. So the baker is going to roll it through what's called a sheeter, creating a flatter and flatter piece of dough as they go. You can see the roller moving down, and the dough becomes flatter and flatter as it's passed through, longer and longer. This is important because we're spreading those lipids really thin between the sheets of dough, so that as they cook, they're going to create a barrier, which in essence creates the puff of the puff pastry. So now he's doing what's called a book fold. This is a technique where we are increasing the layers of the dough, and every baker has their own technique for doing this. Some do a double fold or a triple fold. There's different styles, but what we're doing is creating more flaky layers. So as you see, they're folding it over, and he's going to turn it and pass it again through the roller machine. Now again, here we can see once it's passed through the roller machine, he's going to do another book fold, trimming off any excess piece of dough that doesn't have enough butter in it. If it doesn't have enough butter, it's not going to create the proper puff. So he needs nice solid pieces. He's going to fold it one more time with the trim, fully trimmed off, and then this will go to rest again before it goes through the machine one more time. A properly made croissant can have up to 16 different layers per sheet of dough, and that's about as strong as you can get with the gluten before the gluten strands will begin to break. So you can get a total of 16 folds. So there we see he's got 4 folds. We had 4 folds before that, and he can do 2 more rotations through the machine once it's rested for a total of 16 layers, or 4 folds, 4 folds, 4 folds, 4 folds, 4 folds 4 times. Now here we have bakers that are shaping bread. So they're taking bread which has been fully formed and are what's called a pre-shape. So this is the initial shaping. So once it has fermented in bulk, they're going to give it its first pre-shape. And this just sets the size, and then it's going to rest. You can see that it starts as a blob and they begin to stretch the gluten molecules. This will determine how the bread puffs and what its final shape will be. So the breads are getting their final shape before resting overnight. First thing they're going to do is degas, which is pressing and pushing all the air out of the breads. And now she's creating tensile strength. using those gluten molecules. They're going into a little bit of a cornmeal and durum flour dusting, and then they'll go to rest in those couches before being baked. So again, these are low moisture, antimicrobial muslin fabric from France that helps the bread to rest without absorbing too much of the moisture, and that's really critical as the breads rest so that they don't dry out. And you can see that strength right there. All right, so the dough has mixed. The dough has rested and shaped and fermented. And now after an overnight proofing in what's called a couche, which is a muslin cloth, very specific, French, and it does not absorb a lot of the liquid. So it's very important so that it stays nice and dry. We're going to get the breads ready to go into the oven. So the baker is placing them on the peels and dusting it lightly with flour. And they're going to score them. Each baker's score is unique and important because it controls the direction that the bread will rise. And we can see that these are wonderfully proofed. So if I just poke it, it springs back. It's not getting a sharp indentation, which would mean it is overproofed. And it's not, you know, too puffy. So it's a great spring back, and that's a great indication that the yeasts have done their job. There's lots of air in there. Quick diversion. So this is a dough that has only had one pre-shape and hasn't had enough time to fully ferment. And we can see that when I press it, that fingerprint stays there, unlike the fully proofed dough we just saw. This means that the yeasts haven't had time to expel all their gases yet. And here we're loading up the breads, and we're going to watch as they go into the oven. This is a hearth wood-fired oven, so we've got some real thermoregulation happening here. In this oven, there are 6 inches of brick mass all around. And we use it like a battery, so what it does is it supercharges with heat, and that heat is what is used to cook the breads. So the oven is fired with wood the day before the bake, and there's so much heat and energy created in that fire that the bricks actually hold all of that energy. So as these cold loaves of bread enter the oven, what they're going to do is draw that energy, just like a battery, from the bricks, and it is going to move into the bread and create steam. So what we're doing here is heating up the water molecules within the bread at a very rapid temperature, and we know that the boiling point of water has a very high boiling point, so we need this to be really hot in order to get that quick puff. So the yeasts are going to release their CO2 gas as they are heated up. They go into rapid acceleration, and the water begins to vaporize, which creates pockets. Now, if we don't have proper gluten formation, those water pockets are not going to have anywhere to go. So they will just escape and the bread will fall flat. So the formation of gluten is critical to holding the bubbles in the bread. So as the water evaporates, those bubbles are formed, which gives us the texture of bread that we know with its aerated pockets, and it begins to dry out. If the water evaporates too quickly and there's not enough moisture in the room as it is baking, then the bread will end up very dry and crumbly because osmosis will happen too quickly. And in trying to stabilize the environment and move from what is a very hydrated dough at around, what percent is this hydration?
70.
This is 70% hydration. So about 70% of the weight of the dough is water. So the 70% hydration means that it will move from 70 to much less as it bakes. And if we are in an environment that has very low moisture, the bread will dry out too fast and it'll become very hard and dense. So if we want a soft, chewy bread, we need to control for moisture as well. Now, Ben is scoring it using a tool called a lamb. It's a razor blade on a handle, and the score is really critical to the opening of the bread. So this allows a place for steam to escape, and it tells the bread where the bread can expand. And this is going to dictate the final shape as well as the texture. So if we take a look right here in one of these scores, we can see gluten. These strong strands are the gluten holding the bread together, and we can also see the air pockets develop from the yeast as they're fermenting. And again, this is a wild yeast fermentation, so it's less controlled than if it were a mechanical fermentation. Oh, look at those beautiful air pockets and the gluten strands. These are going to be great loaves of bread. We can also see that they have no color. As they bake, they're going to get color. And he's placing the breads into the wood-fired oven at exactly the precise location so that they're going to bake perfectly. They'll bake for about 30 minutes, 30 minutes total. And it's around what temperature? Around
670.
Around 670 degrees Fahrenheit. All right. All right, folks, remember those loaves that went into the oven to bake? It is time to rotate. So we can see they're super pale. They're definitely puffed. So this is the first half of the bake. They've got almost no color. And the baker is going to choose where they're going. Now, spots closer to the wall are going to be hotter because they have more bricks, so more thermal mass. Obviously, in the wood-fired oven, thermal mass is important because it is what helps the breads to bake. So our baker is going to switch them, move them from one location to another to get closer to the heat source, which is the wall. So in this case, the wall is providing the heat, and we can see the breads. Beautiful. That one's starting to brown a little bit. And that's the Maillard reaction. So in flour, there's two main components. There's protein and starches, and we know that starches are in the carbohydrate family, so they're composed of sugars. So as the protein, which is the gluten, and the starch come together over high heat, we get the Maillard reaction. So anyone who doesn't like the crust of bread, y'all crazy, because that's where all the flavor is. Okay, so I want you to focus up on the top. The baker's just released the flue of the oven, and we are seeing the steam from the bread baking releasing itself from the oven chimney. And this helps the breads to brown. This is the final step in the baking. The breads are ready to come out of the oven. They've steamed, and then they've had time to brown, developing that wonderful Maillard reaction on the outside. And here they are, the final country white loaves. Last but not least, before we end our lecture, I'd like to return to the viennoiserie, which is the flaky pastry dough. So we can see here the raw pastry dough and the layers in there. And as they bake, those layers begin to separate. The butter acting as a shield, keeping the dough from connecting and creating flaky pastry layers, and also the water in the butter creating a puff. So making sure that your butter is very chilled as it bakes is critical, and we can see here really wonderful layers in these final croissants. All right, it's time for a bread recap. What did you learn? One thing that you learned about breads that you didn't know before. Great. Now, what gives bread its strength, its elasticity, and its plasticity? What molecules give bread its strength? Gluten. Gluten, composed of glutenin and gliadins, 2 amino acids that form up together and give bread their strength to hold the air bubbles. Now, why is steam important when baking hearth wood-fired breads or any bread cooked at a high temperature? Why is steam important? Yeah, it helps with the thermoregulation and it helps to slow down the osmosis. So if the ambient room humidity is much lower than the humidity of the bread, osmosis will happen too fast and you'll end up with a very dense, dry bread. But if you're able to inject steam and you're able to change the humidity ratio around the bread, you're able to actually have a much better product with better spring and better airy bubbles. And finally, what creates the rise in a natural bread product? What molecules or beings create the rise in a natural bread product? That's right, it's yeasts, just like our wild yeast culture. And finally, let's talk about cheeses. So what goes better with bread than cheese? Now, what is cheese? Cheese is a fermented product. Today's lecture is all about fermentation. So in the case of bread, where we're really relying on yeasts to do much of our fermentation, with cheese, we rely heavily on bacteria. And this is one of the few times when we actually want to create curds. So we want our proteins to curdle. And in the process of curdling, we create a cheese curd, which can then be stretched, formed, shaped into different kinds of cheeses. But before we get into that, what is cheese actually? It's a combination of milk, bacteria, rennet, and salt over time. So if each of these factors play into the cheese, if we change one thing in each of those factors, we can end up with a completely different cheese. So depending on how long it ferments or what kind of milk is used, what bacteria is used, if the application of rennet is accessible, and how much salt a product has, all these factors can change cheese, which is to say that the world of cheese is absolutely huge. There are so many cheeses. Look at all these different kinds of cheeses. So if you're used to going to the supermarket and picking out the same few cheeses over and over, cheddar, Swiss, Havarti, Munster, you're missing out on a wide world of cheese. So before we get into some specifics, what makes them different? The application of rennet. So rennet is an enzyme which allows cheese to be a better stretchy melter. And this acts on the mycele of the outer cheese casein protein and allows them to stay together, giving that stretch that, as they say in Italian, filare, the stretch on that cheese. So the first cheese we're going to explore is American cheese. American cheese is not cheese. American cheese is actually a milk product. So if you read closely the label of American cheese, it's a mild, meltable, stable concoction of natural cheese bits mixed with emulsifying agents to make, in the language of the law, a homogeneous plastic mass. And we love it because it melts really well. It has a lot of fat, so it's very mouth coating and filling, but it's not actually cheese. Now, there are some other fresh milk cheeses, like ricotta. In ricotta, the difference with this is there's no bacteria. So in this application, it is still a cheese. It is fermented. It can be made fresh or salted, and the application of salt will create a completely different product called ricotta salata. But what it is the whey from other cheeses is then collected and an acid is added, which causes curd formation, as we know, as an acid is added to proteins. Those curds are then collected and we create ricotta, meaning recooked. Now, a stretchy melter like mozzarella, this is going to be a fresh cheese with no bacteria. So in this application, the one thing that we're changing is that bacteria is not added. It is not a lacto-fermented cheese, but it is separated into curds. Rennet is added, which makes it a super stretchy melter, and it is one of the most diverse cheese bases, which can lead to other cheeses, like a low moisture mozzarella, which is the one you get from the deli, nice and sliced. We have a stracciatella, a burrata, caciocavallo, provolone, and scamorza all yield from mozzarella. So depending on how long they are aged, dried, salted, smoked, or cured, they will turn into one of these different cheeses. All right, one of my favorite cheeses are the Bloomy Rind cheeses. These are fresh cheeses, usually about 3 to 6 months old. And what happens here is they go through a process of being inoculated with a bacteria or a mold on the outside of the cheese. So these ripen from the outside in. Usually they're coated with Penicillium camemberte. If it's a camembert cheese, there's a clue to that in the name of the bacteria. And during this, lactic acid is removed, and the ammonia content can increase the pH from 7 to 4.7. So it becomes very acidic. And that can be the sharp tang or the funk of this cheese. And a product of all Bloomy Rind cheeses is this kind of strong smell, but that can be really addicting for certain people. So there are cheeses in France that have a very pungent smell. There are generally raw milk cheeses inoculated in this style, and they can be very yummy and tasty. I like them. So now we can talk about cheddar cheese. Cheddaring is a process that cheese undergoes. So you can make a cheddared style cheese, even if it is not a classic cheddar. This is the original cheese made in the colonial United States. It's very hardy and it can withstand temperature changes, humidity changes. It's one of the most predictable cheese process making. And what they do in this is they press the curds and they salt them at the same time. And then they are allowed to age. Usually Streptococcus thermophilus is at play, as well as Lactobacillus bulgaricus, which is one of the same yeasts that are in our yogurt. So it must undergo cheddaring in order to be considered a cheddar. And it's a very common method of making cheese. So Colby Jack is also a cheddared cheese, in addition to what we think of as a classic cheddar. Now, cheese with eyes. These are cheese in which the bacteria has been added after the lactose fermentation. So the point at which the bacteria or inoculation is introduced to the curds can also change the final product. This is like a Swiss cheese. And in this, the lactate is converted into ethanoate, propanoate, and CO2. And as they collect, they form the eyes. So a young Swiss will have very small eyes spread throughout the cheese. And an older Swiss will have bigger eyes collecting into larger formations and holes. A cheese which was supposed to have eyes and developed without them is technically known in the industry to fromagiers as a blind cheese. So if it was supposed to have this lactic fermentation and for whatever reason during the process it didn't go properly, it's a blind cheese. Another wonderful funky cheese, blue cheese. Blue cheese is one of the most chemically complex cheeses. Scientists have been unable to replicate the flavor of blue cheese artificially. So there is no artificial blue cheese flavoring because it has so many aromatic molecules which make up its unique composition. And it is inoculated with Penicillium roqueforti, which is a sheep's milk Roquefort cheese. The process that it creates. And what happens during it is it's first formed into a block, and then the cheese is needled, and a sharp needle syringe or a large probe is inserted into the cheese during the ripening process, allowing oxygen in, which allows the bacteria to grow. So the inoculated bacteria creates that traditional blue veins throughout the cheese, and the decarboxylation produces these methyl ketones, which have the blue cheese odor. Blue cheeses, unlike the Bries, ripen from the inside out. So as the oxygen is introduced, they ripen from the strongest point of the blue cheese will be the middle to the outside where the softest point of the blue cheese will be. Now, depending on how much bacteria is introduced, the fat content versus the protein content, and all of these factors, time, how long it is aged, at what temperature, will determine if you're dealing with a funkier blue cheese or a lighter blue cheese. And finally, the grand pumbaa of cheese, Parmigiano Reggiano, Parmesan cheese. This is a controlled substance from Italy. So in order to be called a true Parmesan, it must come from a specific region in Italy and undergo certain processes. It is so specific that it actually controls the economy of the country, and can be used as an economic lever. And it's made from the previous day's whey. And what makes Parmesan so delicious is that it has some of the highest levels of naturally occurring glutamate. Glutamate being the molecule that our mouths perceive as savory. So if you've ever gone to one of those pizza slice shops that have, the dollar pizzas, and it's kind of a bland, cardboardy pizza slice, I bet you grabbed some Parmesan. And the reason you're doing that is you're literally trying to shake umami flavor onto your pizza, trying to wake up, guys. So that is about Parmesan. And one last fun fact, when you go into a cheese shop and you try a cheese that has little crunchy bits, as an aged Parmesan does, a mimolette does, a lot of the aged hard cheeses will have that. That is called a tyrosine deposit. And what that is a protein which has tyrosine fully begun to unravel, and it leaves these small crunchy deposits behind. So I hope you enjoyed today's lecture. Lots of bread, lots of cheese. Now it's time to do a quick cheese recap, and then I will lovingly release you to the wild. There are certain factors that affect how a cheese is produced. Can you name at least 3 of them? Name at least 3 factors to a cheese's production. Remember, cheeses are milk, bacteria, salt, over time. So as any of these factors are changed, they're going to affect the final product. Okay, what makes a cheddar a cheddar? Can you describe a cheddar cheese? Yeah, the cheddaring process is pressing curds with salt into solid blocks and allowing them to ferment. Can you give me an example of a stretchy melter? And can you explain why this cheese stretches? What's different chemically about these cheeses that allow them to stretch? Excellent. Rennet is added to the cheese in the cheese making process, and this allows them to stretch or not. I hope you've enjoyed today's lecture. If you have any questions, now is the time to ask it. Any questions? Anything you're unsure of? Great. I'm grading your term paper drafts and will have them back to you today so that you can have my concise feedback. Please make sure that you note that your final term paper is going through Turnitin. So it will be checking for plagiarism, and anything above 30% matching will deduct points. If it is above 30% matching and you have not quoted your sources, you will be cited for plagiarism and will receive a grade of 0. So please don't do it. Write in your own words. It's easy to see when you're copying and pasting from the internet, but what I'm looking for is for you to explain to me what you've learned about your topic in depth, using supporting materials from the research that you've done. One way I like to help people do this is to actually record yourself. Record yourself speaking and explaining to someone what you've learned about whatever your topic is. So if your topic is cheese, you can explain in detail the cheese making process, and this will help you to synthesize those thoughts on your own. Once you've recorded it, you can translate it into text, go in and clean it up. Make sure you check for grammar and check for spelling and check for citations. But it's a great way to get your thoughts onto the page and make sure that they're your original thoughts. If you have any questions about your term paper, not your final project, but your term paper, now is the time to ask them. Have a great day.